Hi everybody. The last time we were together, we were talking about basic issues of probability. Let's continue that conversation. If we're going to learn about inferential statistics, we know that inferential statistics is built on the language of probability, so we need to understand some of the basics. What we're going to do in this particular segment is focus on the law of large numbers. As I mentioned here, the law of large numbers holds a special place in the heart of statisticians. It's just kind of interesting, and it also leads to some errors in logic that many people have. And hopefully after you graduate from this class, you won't fall prey to some of these unrealistic types of thinking. So let's jump right in. The law of large numbers is often just known as the law of averages. What we're essentially talking about here is that when long-term trends are clear, individual events can often be unpredictable. So for example, eating healthy and exercising should prolong a person's life. When we look at that over the long run, that's true. However, when we look at an individual event like my cousin, when I was young, I had a cousin who was older than I was. He was 28. He was in great shape. He had his whole life ahead of him. And he died. In fact, he died while he was jogging. I mean, he was in that good of shape. He exercised every day, and he had some aneurysm, essentially. And how do you make sense of that? It doesn't seem to go along with the basic trend. Well, as I mentioned, individual events can be unpredictable. Same thing here. About 8 years ago, I started to get more interested in bowling because my wife and her family were interested in bowling. And I bought a new ball. And that day, that first game that I bowled a 236, which is a pretty darn good game. And that was very unrealistic for me because my average at that time was just 130. So you'd predict that I would bowl somewhere around a 130, but I bowled so much better. Again, individual events can be very unpredictable when we look at them in terms of long-term trends. But when we're talking about the law of large numbers, what we're talking about is over a long period of time, after repeated trials, the results should really start to approach the truth. So, for example, going back to these examples right here, in general, when people eat healthy and they exercise, they on average are going to live longer than people who don't eat a healthy diet and do not exercise. And people who bowl averages of about 130, they're not going to be bowling many games at 236. It's just very unlikely because over time, the results will approach the truth. Let me give you an example based on a simple type of example that we've talked about previously, like flipping a coin. So, for example, the probabilities of flipping a coin and having it come out heads should be 0.5 because all there is a head and a tail on a coin. And results should approach 0.5 as our sample size increases, as we flip that coin more often. So for example here, if I flip a coin 6 times, the results can be relatively unpredictable. I mean, in this particular case, I flipped the coin 6 times, and it looks like 3, 4, 5 of the times I got heads. Now, if the results over the long run should be 0.5, why am I finding that the probability of flipping a coin and finding that it's heads is 0.83 because I had 5 heads over 6 total outcomes equals 0.83. Well, the sample size was really small. But if I were to flip that coin 6 more times and then 6 more times and then 6 more times, I should find that the results approach a value of 0.5 as that sample size increases. So it's likely to look like this after I flip the coin 6 more times. Now I have a sample size of 12. I've got, 5 heads from the first 6, now 6, 7 heads. Now I have 7 out of 12 coin flips resulting in heads, and that equals a probability of 0.58. So the bottom line is I'm getting closer to that true probability of 0.5. So this law does apply when we talk about it in its purest form to independent events. And you might recall that independent events are trials in which one event, one trial, has no bearing, no impact on another. So when I flip this coin, that has no bearing, no impact on the outcome of when I flip this coin. And I can have 2 heads in a row. That still has no bearing, no outcome when I flip this coin. That means they're independent events. They're not related. Let's go over a couple more examples. Let's think about roulette. Let's start thinking about some casino games. You know, now in Columbus we have a casino, so we should probably be familiar with some of the probability theory that underlies some of these games. Let's think about a roulette wheel. This is an interesting example. A roulette wheel has 38 numbers on it. You can see we've got all these numbers. Some of them are black, some of them are red, and there are actually 2 of them that are green. So there are 18 black, 18 red, and 2 green. And let's just assume that each is equally likely to be a winner, because they are. The way they construct this wheel is that it's equally weighted. These are constructed, these little numbers, they have little chambers, little walls separating each one. So each one is kind of like a little chamber where the ball can rest. And they're constructed with very close tolerances so that no one number is more likely to come up than the next. Let's just assume that that's true. So what's the probability of winning when you pick a red number? So you put your money on red. There are a lot of ways that you can bet. Let's say you pick that a red number is going to come up. Well, we should be able to do this based on what we know about basic probabilities. We can compute a theoretical probability. Remember how this works. We can look at the number of ways that red can occur. We know there are 18 different red numbers over the total number of all outcomes. And we know that there are 38 numbers overall. So we've got 18 divided by 38. And if we did the simple math right there, we would find that the probability equals 0.47. So the probability of winning with a red number is 0.47. Well, let's think about it this way now. If the wheel spins 100,000 times, how many times will a red number come up, just in general? Well, we can take that probability, 0.47, and use that to answer this question, because 47% of the time we would expect to find a red number popping up. And if we spin that wheel 100,000 times, well, we should find that 47% of the time we're going to find red. So the question is, what's 47% of 100,000? Because according to the law of large numbers, that proportion over so many different spins should start approaching the truth, the real probability. If we take 100,000 and multiply by 0.47, we'll find that 47,000 times we should expect to find a winner on a red number. All right, so we're just trying to understand this just in general. Now, with that in mind, let's see how some thinking can go awry when people aren't really thinking appropriately about this law of large numbers, or the law of averages. So let's talk about some instances in which people kind of break this law with regard to how they think. So let's just remind ourselves, after repeated trials, results should approach the true probability of any event. And we want to keep in mind, too, that even though that this is true, each trial is still independent of the others. Well, sometimes people don't take this into account, and that leads to a very interesting fallacy. Let's continue to think about roulette. Let's just assume that we're at the casino. And when that wheel spins and there's a winner, you'll see next to the wheel there's a board, an electronic board nowadays, that shows the winner, and it'll show its color. So we can see at the last spin there was a red 7 that came up as the winner. And then in the next spin there was a black 22 that came up as a winner. And this is just so people can have kind of a running tabulation of what those winners were, because they might want to use that information to place their bets. And already that's what a sucker would do. That's not smart for reasons that we'll get to in just a minute. But now let's say that wheel was spinning and a red 5 came up, and then a red 34, and then a red 3, and then, wow, another red, a red 12, and then a red 32. So we have this streak going on of red, and we know that approximately half the time, 47% of the time, we should find reds, and 47% of the time we should find blacks. I mean, we just found this huge streak of reds. And this is where some gamblers start to think black is due. So my question to you is black due? The next time we spin that wheel, is it more likely that we will find a black number as the winner? And before you kind of give me an answer to that question in your own mind, just think to yourself, would you bet $1,000 on it? Are you really that confident? And I'm hoping that you're not that confident. And I'm hoping that you're realizing that black really is not due. This is what we call the gambler's fallacy. It's a mistaken belief that after some type of streak, like we have in this case with a variety of outcomes being red numbers, that somehow the black number is due. But we need to keep this in mind. This is why I was saying it's a sucker's deal. It's not the right way to think about this. The probability that any particular spin is going to turn out to be red or black is 0.47 on every single spin. So on this spin right here, we don't know what's going to come up next, and a lot of you are thinking black is due. The probability is still 0.47 that it's going to come up red, or 0.47 that it's going to come up black. When it comes down to red or black, the probabilities are exactly equal. Why is that? The wheel has no memory. What does the wheel know about this streak of red numbers? Is the wheel trying to do something now to correct for it and produce a black winner? The wheel has no memory. Every single spin is independent of the next. So how do we account for these long streaks then of red winners? Well, the answer isn't very sexy. The streaks like this just occur naturally with random events. Really, people think that they should see like red, then a black, then maybe a black, then a red, then a red, then a black, then a red, then a black. That's not what we see with random events. With random events, we often see red going to black, black going to red, but sometimes we see black, 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 red, black, black, red. It's a random sequence. It's a random sequence. And in any random sequence, yes, we often do find streaks. But on any given trial, the probability of finding a red or a black is 0.47. If you're thinking about it otherwise, you are falling prey to the gambler's fallacy. Let's go through an example here and see if we can better understand the law of large numbers. Imagine a coin toss game, and imagine that you win $1 for every heads and you lose $1 for every tails. After 100 tosses, you're $10 down because you've tossed 45 heads and 55 tails. So remember, you're winning $1 for a heads, but you're losing $1 for the tail. So you're down $10. You continue playing until you've tossed the coin 1,000 times. And at that point, you've gotten 480 heads and 520 tails. So now you're down $40. And what seems strange is, proportionately speaking, we have more heads now, but you've lost more money. Is this consistent with the law of large numbers? Let's think about it. Let's break it down. Let's think about the first part of this question where we're given this information about after your first 100 tosses. After 100 tosses, we had 45 heads out of 100. So the probability of finding a heads is obviously 0.45. Now we know the true probability is 0.5 because you can just get a head or a tails. So let's see what happens after 1,000 tosses, because if the probability is increasing, then this is consistent with the law of large numbers, because as we have more and more trials, the probability of finding a head should approach 0.5. In other words, it should approach the true probability as our sample size increases. And that's the case because after 1,000 tosses, the probability of finding a heads is now 480 times out of 1,000, which is 48%, or a probability of 0.48. So because heads is approaching 0.50, the results are indeed consistent with the law of large numbers. But this is where it gets kind of interesting. Despite the probability of heads approaching 0.5, I mean, we're getting close to heads coming up half the time. We're still losing more times than we are winning. So we have continued losses. So it's not like we ever made up for that $10 loss. Plus, we're continuing to lose, and we have, of course, tossed that coin many more times. So, of course, our losses are adding up. So we need to keep in mind that this number might not ever exceed 0.50. It's not like if we keep tossing that coin, eventually we're going to turn out to be winners. The true probability is 0.50. And over time, this probability should approach 0.50. It's not going to necessarily exceed it. You're not necessarily going to recoup your losses and walk away a winner. That would be consistent with the gambler's fallacy. Let's take this discussion of the law of large numbers and put it into play a slightly different way by computing expected value. I think it's really very interesting. Let's look at an example that again involves some gambling. So expected value is really just a weighted average of all possible events for some type of situation, like playing a lottery or playing some type of casino game. Expected value tells us on average how much we can expect to gain or lose, and because of that, it really makes most sense to think about it over the long run, because remember, individual events can be very unpredictable. And this is how it's related to the law of large numbers, because over a long series of events, over the long run, the expected value should hit what we compute, should hit a basic probability. So let's consider that the following probabilities are true for buying like a $1 lottery ticket. You know, when you buy some type of lottery ticket, there are usually several ways that you can win. That's what we're talking about here. So just imagine that there's a 1 in 5 chance, and that of course would be a probability of 0.20, 1 divided by 5, to win a free ticket, you know, free $1 ticket. And here's another way that you can win. There's a 1 in 100 chance, so that's 0.01 in terms of probabilities, to win $5. Okay? There's another way that we can win. There's a 1 in 100,000 chance of winning $1,000. And this is realistic because, of course, $1,000 is quite a bit of money to win after you invest just $1 in a ticket. So the probability is very, very low. And let's just make sense of all the decimal places here. We've got 1 in 100,000. If our 1 was right here, that'd be 1 in 10, 1 in 100, 1 in 1,000, 1 in 10,000, 1 in 100,000. And the probability is even lower, 1 in 10 million to win $1 million on this lottery ticket. So 1 in 10, 100, 1,000, 10,000, 100,000, 1 million, 10 million. The probability is 1 in 10 million of winning $1 million. So here's my question. What's the expected value of a lottery ticket? You're going to pay $1 for this ticket. What's it really worth? What's its expected value? What can we expect out of it over the long run? Let's create a little table and we can fill in the expected values. The expected values are very easy to compute. We just take the value that we can win or lose and multiply the probability of winning or losing. So value times probability. And then we're going to add that up. So winning a free ticket, it costs us $1 to play the game, of course. And in this case, we would win a free ticket that is worth $1. So $1 times a probability of 0.20 is going to equal 20 cents. And of course, that's pretty obvious. Let's just look at our calculator real quickly. We'll go over some of the other ones that are more difficult to compute. But here I just took 1, of course, and multiplied by 0.20, 20 cents. Okay. So in this case now, we've got a chance of winning $5. Now the probability is only 1 in 100, 0.01. So we can compute that real quickly as well. In this case, we would have 0.01 times $5. That equals 5 cents. So you can see we're computing the probability for each event and then multiplying that probability by how much we could win. I could win $5. I have a 1% chance. So it's like each ticket then has a 5% value for winning that particular prize. And we just keep adding those up. So let's add our 5 cents in there. There is a very small chance, we see the probability in here, of winning $1,000. Let's multiply that out. So here I have 0.0000, that's 4 zeros, 0.00001 multiplied by $1,000. Sorry, I think I've got 10,000 in there. Let's try that again. 0.00001 multiplied by $1,000. So of course we have to be careful. That will equal 0.01. So the expected utility, the expected value of winning $1,000 with the probability being so low on a $1 ticket, it's just contributing like another penny to this overall expected value that we're computing. So let's go ahead and list that in real quickly. That's contributing a penny. And what about this $1 million prize? We had like a 1 in 10 million chance of winning. Let's compute that real quickly. Find our calculator again. So we have point, let's be really careful, 0.0000001 multiplied by 1 million. So that's 1,000,000 equals 10 cents. All right, so 10 cents is added to the value, the expected value of that ticket. Let's go ahead and stick that in. All right, so at this point, we can add up these expected values. 20 cents plus 5 is 25, 26, 36 cents. All right, but there's something we need to keep in mind. The expected value that we can win on each ticket is not actually 36 cents because there is something that we forgot. And that's why I left some room in here. And that's that we need to purchase the ticket just to play. So to purchase the ticket, how much is it going to cost us? It's going to cost us $1. And the probability of losing that dollar is 100%, isn't it? The probability is 1 because in order to play, we have to pay that $1. It's going to happen every time. So what is the expected value for this particular portion? Well, we've got $1 times the probability of 1. So that's -1. We're losing $1. So now we need to subtract that dollar. So now we've got all of the outcomes. We've got every single thing that we can win. We've got every single thing listed that we can lose. And now we can compute the overall expected value of buying this ticket. And in this case, it comes out to -64 cents. So what's that really telling us? It's easier to understand this over the long run. Averaged over the long run, you should expect to lose 64 cents for every lottery ticket that you buy. You know, you're going to win sometimes, but you're typically going to lose. And over the long run, you would expect to lose 64 cents for every $1 lottery ticket that you buy. So, for example, then, if you buy 1,000 tickets because you like to play this on a regular basis, you would expect to lose about $640 over that long run. We can compute these expected values for almost anything as long as we know what all the options are in terms of winning and losing, and as long as we can at least estimate the probabilities. Then we can compute a table like this for anything. All right, my friends, that was the key content from section 6.3. Real quickly, let me just talk about section 6.4 and 6.5. In section 6.4, there was a discussion of risk and life expectancy. And it was actually a very interesting section, and I'd like you to read it, but it's very straightforward. It provides some very interesting statistics, so we probably won't spend any time on it in class. Just please look it over on your own. And in section 6.5, there was a discussion of combining probabilities, and everything that I wanted to cover from that section, I already covered along with the material in section 6.2 and in that video. So for example, there was a section about either or probabilities for non-overlapping events. That was what Rule 2 was. And we also covered and probabilities for independent events. That was Rule 3. So we've already covered that stuff from that section. All right, my friends, that is the key content from section 6.3 through 6.5. And for now, that is all.